Okay, hi everyone. So today I'm going to be talking about covariate measurement error. So that's when basically your covariates or your independent variables are not measured perfectly, but rather you know that they're probably measured imperfectly with some kind of error associated with it. So this should hopefully be a short and sweet seminar series or seminar session. So let me get right into it by asking you, what do you think this is? So I'll give you a few seconds to think about it. I'm sure it's very quickly coming to your mind. Yes, it is you, it is me, it is all evil and all good in this world. It's basically any researcher when they have a p-value less than greater than 0.05, right? So if you're in this situation where you have this hypothesis that you want to test, you really want it to be less than 0.05, but it isn't, then you're probably pretty sad. You're probably not in a good mood, probably a bad day. But what if I now told you there is a way that you can potentially get your p-value to under 0.05 for free? Well, then I'm sure listening to that, you probably have a reaction something like this. It's like a caveman that has just found fire. So, okay, now that everyone's hopefully paying attention, let me talk about how you can potentially do that. So I'm going to start. So this motivation slide has a bunch of maths and equations just to set up what I'm really talking about in a more solid way. You can get the rough idea of what I'm talking about without necessarily understanding the equations, but I'm a bit of an equation lover, so I'll go ahead and do that. So suppose you have this linear regression, this simple linear regression model where you just have an intercept alpha. So you assume that your responses or your outcomes y follows this equation where it's some intercept alpha plus some slope beta times some independent variable or covariate that we call x plus some random error here, which for the purpose of this talk, I'm just going to assume that's normal zero with mean zero and some variance sigma epsilon squared. So when you have this simple linear regression model, a typical way that you might try to estimate the true slope beta with the data is using least squares regression or maximum likelihood. And that if you do that, basically you'll get this equation here, which is your estimator is basically given by that formula there. And so a property of this estimator is that as your sample size increases, as you have a really large sample size, as your sample size tends to infinity, then this estimator is actually what we call consistent for the true parameter beta. So it actually converges in probability to this true parameter beta there. So what that means is as your sample size gets really large, you should, if you use this formula, then your estimate, beta hat, should be very close to the true actual value of the slope for your independent variable x there. Okay, so that's all good. But so here's the problem, which is what I'm going to be talking about in this talk. So the talk is about covariate measurement error, and what I mean by that is this at least for the purpose of this talk, it's this very specific thing where instead of observing the true covariate x, you instead observe some error-contaminated version of x. So this zeta I here is just some normal mean zero constant variance random error that's associated with W. So instead of observing X, you observe this error-contaminated X, which we call W. So, okay, so now you can imagine, like, instead of having X, you actually only observe W. And what would you do? Well, naively, you might just plug W into this formula instead of X, right? Kind of intuitively, maybe that's something that you would try. In fact, that's what you would do if you didn't know that your covariates were actually contaminated with error. But if you do that, so I'm going to define this new estimator beta tilde, which is basically the same formula as up here. So it's just the least squares formula for estimating your slope beta. But here I have W basically instead of X, wherever X appears. And the problem with this estimator beta tilde is that it actually converges the probability to this value over here. So it's consistent for something that's actually not your true slope parameter. So in particular, you can see because sigma zeta squared and sigma x squared are always positive. So you'll actually be consistent. You'll be estimating basically something that's smaller in magnitude than what your true slope beta actually is. So you'll be basically shrunk towards zero. You have a bias towards zero that you don't want. And this is called, in the literature, this is called the attenuation bias. Obviously, you don't want that because it's biased. So here's a list of some common situations where you might find you actually have error in your independent variables or your covariates. So at the risk of just reading off the slides, it's pretty common when you have self-reported data, when you have any sort of instrument limitations. If you're using a proxy variable, if you're using, for example, education level as a proxy for socioeconomic status, there's recall bias, reporting bias, there's all that stuff. Technology-based data. So, for example, if you're trying to measure stuff like temperature. So, in my understanding, so I have a small background in a bit of spatial stats, and geostat, that kind of thing, and something like temperature is often associated with not being measured perfectly. A covariate that's not measured perfectly. There's also experimental design limitations, as well as finally any sort of two-stage model where maybe your covariates in the second model are estimates from the first. So for example, if you're trying, let's say you do a factor analysis or a PCA on your data, and then use those PC scores or like factor scores as covariates in like a second regression model or something like that, then there will actually be measurement error in that. So that's something that you should probably be thinking about. So here's a more practical example. This is actually from my PhD work. So I just included it here to give you a grounded practical example in case you don't have something in mind yourself from your own data. So I'm just going to briefly talk about this. I'm not really going to mention this again after this slide, but in this data, I have this data on some research series. They collected presence-absence data. So they went to a bunch of locations in the USA. And they basically, at each location, they recorded whether or not this certain species of bird, the Carolina wren, was present at the location that they went to. So that's what these dots are. The red dots indicate that the researchers found that species of bird in this particular location, and the beige points represent that they were not found. And you can see the background color of this map is so the top two panels here is about temperature. So this left-hand one is the minimum temperature in the corresponding location, and the right one is the max temperature in the corresponding location. So that's the background color of this map. And importantly, you can see that in these bottom two rows, we actually know for a fact that these temperatures, these minimum temperatures and maximum temperatures, are recorded with some kind of error. And for this particular data, we actually knew what that error was from repeated sampling, from being able to get repeated samples over time, over years of the temperatures at these type of locations. So yeah, so this is a pretty typical example of when you might get covariate measurement error. So let's talk about some solutions. So here are three typical solutions. One is called regression calibration, which is when you try to replace the mismeasured covariate with some kind of prediction of the true underlying covariate, which I called X in the previous slide. There's something called simulation-extrapolation, which is when you add extra simulated noise to your covariate that's already measured with noise. And then you keep fitting your models, keep fitting the model of interest at each point of extra simulated noise. So you might simulate a little bit of extra noise and then a medium amount of extra noise and a large amount of extra noise in your measurement error. And you fit a model each time. You fit the model of interest each time for that, and then you extrapolate back. You can fit a curve to how your parameter estimate changes as you change the amount of noise in your covariates, and then you can extrapolate back to the no error case. So in this talk, I'll be talking about regression calibration and simulation extrapolation and how to do this in just a little bit more detail. There's also likelihood-based methods, which is when you specify a joint model for the outcome, the true covariate, and the observed noisy covariate. So I guess one potential problem with this is that if you really want to make sure that you're getting the right estimate, you're unbiasing everything, then you kind of need to have the correct specification of your likelihood model. So I won't really be talking about the likelihood-based methods in this talk. A caveat for a lot of these methods is that they actually assume that your measurement error, which I call sigma zeta squared, is known or at least can be estimated from the data. So one way that you might be able to estimate this measurement error from the data is maybe you have repeated measures of your covariate, let's say over time or whatever it might be. So that's often required for a lot of these methods. So in that case, in this sense, it's not just like completely for free, right? And you can't get rid of the problem without having extra data or having some extra knowledge about the error. A few methods circumvent this requirement by modeling the true underlying covariate. So you can try modeling the true underlying covariate. So for example, like in my example here, if you try to model, for example, the minimum temperature, let's say as a smooth function of the space. So since you have data, you have information about the locations and space, right? So if you kind of assume that temperature varies smoothly across space, then you can actually model that minimum temperature. In this case, well, as a smooth function of space. But you can also try other things, maybe a smooth function of time, or just some other, you have some reason to believe that your true underlying covariate follows some kind of underlying model that you can fit. I won't be talking about that much in this talk either, but it exists. So firstly, I would like to talk about how regression calibration works. So the main idea of regression calibration is basically you want to, instead of just using the error contaminated covariates W directly, you want to actually try to predict the true underlying covariate Xi, and then use that. So for example, you can try to replace W with this prediction of Xi, which I'll call Xi hat, given by the expected value of Xi given Wi. So this expected value here, at the moment is kind of vague, right? But so what people will often do is they'll assume something about the way that X is distributed as well as how the error is distributed. So for example, if you assume that X is normally distributed with some mean mu X and variance sigma X squared, then you can actually show that the expected value of Xi given Wi is given by this thing here, by this equation. So if you, for a moment, just assume that mu X is actually 0, so if you have like a mean-centered covariate Xi, then you can see that this is, so the mu 0 is just, the mu X has just become 0, and then you have expected value of Xi given Wi is just going to be Wi divided by 1 plus this ratio here of the error variant of the measurement error variance, as well as the variance of your actual true underlying covariate X. So this ratio here is called the reliability ratio. That's just a fun fact. But you can see, because this denominator here is always going to be bigger than 1, because these variances are positive. So essentially this predictor that you have, the expected value of xi given wi, that's going to be a shrunken version of your actual observed error contaminated covariance W. So here's a bit of intuition on why that works or makes sense. So if you recall the beta tilde from this previous slide here, where I use the least squared solution, but with W instead of X, it's given by this formula here, and it converges in probability to this value that is slightly smaller in magnitude than your true slope covariate beta. And so what regression calibration does is, so you can see, because this statement is true, then we also know that if you just multiply both sides kind of by 1 plus sigma zeta squared divided by sigma x squared, then this new estimator here, this thing on the left-hand side, that converges in probability to exactly what you want, which is the true underlying slope or your true underlying covariate X. And actually, that's exactly what regression calibration does in this particular case. So like with the intuition that I just gave, where your prediction, your xi hat is just a shrunken version of wi. If you plug everything in there into the formula, you'll see that the estimator that you end up with is actually just this thing on the left-hand side there. Now here I assume that the xi's are normal, right? And I'm actually also assuming that the measurement error that you have for your covariates is also normal. Now that measurement error assumption, that's pretty common in the literature. But whether or not your true X is normal, that will affect what your predictor expected value of xi given wi is. But actually, I think from what I've seen, often, even if you just use this formula, kind of no matter what your actual distribution of xi is, this formula often actually works decently anyway, because even though it's not the expected, it won't be the expected value of xi given wi, but it is actually still the best unbiased linear predictor for xi given wi. Okay, so regression calibration is obviously, since it recovers this perfectly, it's great for linear regression when your assumptions are all actually met. However, the performance can deteriorate in more complex situations. So in particular, when these assumptions on like how your X is distributed, how your error is distributed, when that doesn't hold. So the second method I want to talk about is simulation extrapolation. So this method is a bit more flexible than regression calibration, but with a drawback that there can still be some attenuation left, especially if your measurement error is quite large relative to the variance of your actual underlying covariate X. So here are the basic steps for doing simulation extrapolation. So in step 0 here, you want to recall that your contaminated covariate Wi is your true underlying covariate xi plus some measurement error zi. And what you want to do is you want to make new covariates wi star here, which is given by your wi, which is already contaminated with error, plus some other independent error there, xi. And then you want to refit the model. So you want to refit your y, your response variable, on this wi, on w star, which is the covariance with extra error that you've just manually added. And you want to do that kind of for a bunch of different variances for this guy here. And then what you want to do is you want to observe how the parameter estimates change as you vary the variance of this xi. And then you can observe how the parameter estimates changes as your error increases, and then extrapolate back to the case of zero error to recover the true parameter. So the way that people often extrapolate back is by doing something like fitting a quadratic curve to how your parameter estimates change as a function of the error. Okay, so a problem with these methods that I want you to think about right now is that they both actually introduce a bit of uncertainty into your parameter estimators. So with regression calibration, there's some variability associated with trying to predict your true underlying covariate, and with simulation extrapolation, it also introduces extra variability through the simulation as well as extrapolation steps. So because these facts are true, then you cannot just use the naive standard errors that you might get from fitting your Y on W, let's say. So inference is something you should be a bit careful about when you're doing this. And both methods will also have extra variability if your measurement error is estimated instead of known. So yeah, you shouldn't rely on the standard naive standard error estimates. However, regression calibration in the setting that I'm doing it in this talk, which is when all those assumptions are correct, that does actually give you the standard error when you fit Y on X. So if you have, in whatever software, your favorite software of your choice, if you fit Y on your X hat over here, which is your predicted X given W, and then you just calculate the standard error, using that model directly, that will actually give you the correct standard error directly. So that's nice in that particular case. And for simulation extrapolation, in this talk, I'm going to be doing it for you in a few slides inside R. And in R, you want to use the SimX package, and that actually adjusts the SimX uncertainty for you automatically. It'll give you have two choices when you use SimX for doing inference. So it'll give you like an asymptotic approximation of the standard error, as well as a jackknife approximation of the standard error. I would probably recommend this jackknife one, unless you have a really large sample size. So here's some sample code for actually doing SimX inside R. So I did a bit of a simulation here. So I simulated 100 data points where my intercept alpha is 1 and my slope coefficient beta is 2, and then my epsilon, the variance of my epsilon there is 1, and my measurement error, standard error is or standard deviation is 0.5. And then I basically just generated everything from normals. So X is standard normal, epsilon's normal, and so Y is also normal. And then W, which is the error contaminated version of X, or the observed noisy covariate, that's also normal. So I had a look at what happens if you fit the naive model. So if you just fit Y on the contaminated covariates W directly. And then I also had a look at what happens when you fit the SimX, the SimX method or the SimX model on that. So the way you want to do that with this particular package is you want to fit the naive model first, and then inside this SimX function, you just put your naive model in here, and then the variable with error, you just put it in there with this name. And you need to give it, the measurement error, which I said needs to be known, or is at least able to be estimated. B here is just the number of times you want to do the SimX. So SimX is a simulation approach, right? So it's random, and B is just the number of times you do the simulation. And lastly, there's this lambda argument here, which is the different values of the extra measurement error that you simulate on top of the measurement error that you already have. So these values like 0.5, 1, 1.5, and 2, I think is a pretty typical default for that. So okay, here's some results from that. So this bit that I'm scrolling right now, that's from the naive model fit of y on w, and you can see that the intercept here seems pretty close to the true value, which is 1, but the your slope coefficient which is of primary interest, you can see that that's quite a lot smaller than the true value 2, right? But when you down here, when you actually do the SimX correction, then it gives you a better estimate. So here, you know, you're going pretty close to 2 now, right? Which is the true value. And the intercept hasn't really changed too much in this case, in this particular case. Now with the SimX, you can, if you just use like a plot function on the SimX object that you get from the package, it will show you this little plot here, which is how your parameter estimates change as you vary the amount of error added, which is controlled by lambda there. So you can see this one on the bottom here, that's the one you're most interested in. This is the slope for x or w, right? So you can see at this point where lambda is equal to 1, sorry, this is 1 plus lambda. So when 1 plus lambda is equal to 1, then lambda is 0, which means you added no extra measurement error. So this is the point, this is the estimate value when you're just fitting y on w. And then as you add more error, you can see that it's kind of slowly tending, well, it's actually tending towards 0, right? And then what you do is you fit a quadratic curve to this thing, and then you extrapolate back all the way down here to 0, which is the case when you have no measurement error. Now, something to notice here is that, so this thing seems to be going down as you increase the error, right? But this thing on top, your intercept estimate, that actually seems to be going up as you increase the measurement error that you artificially add. So something I want to mention here is that even though like the intercept isn't measured with any error, right? The intercept is always just 1. But just because your w was measured with error, or your x was measured with error, that biases not only your slope estimate for w or x itself, it can also bias other things, other covariates that you might have in your model as well. So definitely, like, fixing this measurement error problem is something you want to do, even if it's not the covariate of your primary interest. Okay, so here I did a few more simulations to compare, to actually have a look at the coverage and stuff like that, and to look at how regression calibration does as well. So yeah, in the simulation, I simulated it 1,000 times. I did the same 100, the sample size of 100, but I did the simulation 1,000 times. All the other parameters are the same as that small simulation I showed previously. So so this code is available. The slides will be available. The code will be available later if you're interested in it. But the SimX part and the naive fitting part is pretty much the same as before. For the regression calibration part, this is just basically using the formula that I had in the previous slide. Yeah, so I had to assume that sigma zeta squared is basically known in this case. So let's have a look at what happens. So firstly, so the naive method in this case, so I did that simulation 1,000 times, right? And the mean of the naive method, which is just fitting y on w, that was 1.6. So you you recall that the true value is 2, right? So that's pretty far. You're pretty biased at this point. And your coverage, which I set to 95%, is a lot less than that. In fact, it's not even 10%, right? So you're doing quite badly. But with the regression calibration, it goes back, the mean of that estimator when you correct for it is about 2.01 in this case. So that's doing a lot better than the naive method. And also the coverage is also pretty good. It's more than 95%, but I think it's just it's just because of the way the numbers worked out in the simulations and the random numbers. And SimX here, it's also doing pretty well in this case with a mean over the 1,000 samples of 1.995-ish. And the coverage is also decently close to 95%. So if you have a look at the histograms of those estimators, throughout the 1,000 simulations, you see that obviously the naive one, you're doing quite poorly, like you're barely ever getting any values any close to that, right? Whereas the regression calibration, it looks pretty perfect, right? Because in this particular case, it is actually perfect. It's like the best you can do. So it's very nicely normally distributed around your true parameter value. Whereas SimX, it seems to be doing quite well as well, but you can see them, maybe you can slightly see there's like a bit of a small, tiny bias towards 0 still. So you can see, so in the simulation, I use the measurement error of 0.5 for the standard deviation of the measurement error. And it gave me results like that, right? So, but I did mention that SimX, sorry, this is just another coverage probability plot. But SimX actually tends to perform that as well when you start getting really high measurement errors. So I tried another simulation where I increased the measurement error standard deviation to 1. So I doubled the standard deviation of the measurement error. And now if you try to do the same simulation again, you'll see something like this. So the naive estimator, which is just fitting Y on W directly, it's still doing poorly. It's doing even more poorly than before. The coverage is 0, even though you want it to be 95. For the regression calibration, that doesn't actually care in this particular case how much your measurement error is, because again, it's adjusting it perfectly in this case where everything's normal. But you can see SimX has deteriorated quite a lot just because I increased the measurement error. So now the mean is about 1.5 and your coverage is down to like 30%. So it's doing quite badly, but it is still doing better than the naive method where you're just directly fitting your response onto the error contaminated covariate. So a plot of the histograms looks like that. So obviously you can see what I was just talking about. The naive is doing really poorly. SimX is doing quite poorly here, but still better than that. And regression calibration is still doing perfectly as it would. That's the coverage probabilities. Now, finally, what if you had non-normal covariates and responses and covariate errors? So I tried a few different settings. So here I have one to kind of show you the results for. So when I tried a log normal X with the binary Y and shifted exponential error, so it's quite a departure from those normality assumptions. In this particular case, the naive one is always doing bad, but you can see that the regression calibration is no longer doing really perfectly at all. In fact, it's only a very small improvement to the naive case, whereas SimX is kind of doing slightly better than the regression calibration, as well as the naive case. So you can see it with these numbers here a bit more clearly. So the naive, so my slope was still 2 in this case, my true slope, and the naive was giving 0.7 on average. The regression calibration was giving 0.9 on average, and SimX was giving something a bit bigger, which is 1.2 on average. And not only is the SimX point estimator a bit better than the others, but the standard error estimate is also a bit larger, which is really what you want in this case, because you're not really that confident in your actual estimate. So basically not only is the naive and regression calibration doing worse than the SimX in this case, it's also doing worse more confidently. So that's quite bad, right? And just some final remarks that I want to leave you with. So well, in conclusion, regression calibration and SimX, they're both popular methods for adjusting for covariate measurement error, but they do need your measurement error to be known or at least able to be estimated from, for example, from replication data. So if you have several observations of your x's, independent observations of your x's. Right? But so here you might, come up. Well, a question might form in your mind of if you do actually have replication data, why don't you just try to use X bar? So you take the mean of your x's over the independent samples and then try to use that as the covariate instead of your error contaminated W that you might have. Well, you can actually do that, but and asymptotically that's good. Then you don't asymptotically once you have an infinite number of replication cases for each of your x's, then you don't need to actually adjust for measurement error if you just use X bar as your covariate. But in finite samples, there is still measurement error remaining, which if you do know the measurement error, then you might as well adjust for it, right? Now, SimX is actually considered the gold standard. So I think I've been hinting at that a little bit, although the simulations might not convince you that much. But in the literature, just because it's quite hard to really get right all of those assumptions that you're making about the error, about how your x's are distributed and stuff like that. In the literature, SimX is kind of considered a gold standard, even though it's not perfect. But it can definitely still perform poorly when measurement error is high. But that doesn't necessarily mean you shouldn't do it, right? Because that's still doing the SimX is still better than not doing anything at all when you know you have measurement error in your covariates. So it's not a magic bullet, but it still helps. And one thing you should be careful of when you're using these techniques is you should be careful when doing inference. So in particular, confidence intervals and p-values. So like if you look back here in this example, say, like if you made confidence intervals using this kind of thing, the coverage will probably be quite a bit less than your nominal coverage that you want. But that's kind of just life. Like you still want to be doing something instead of nothing, right? But it is something to be aware of that even if you corrected it, it doesn't mean that your confidence intervals and p-values are necessarily going to be perfect now. And here, just final 2 points to leave you with, maybe in a future seminar that I haven't talked about at all here. What if you have categorical covariates? What if you have multiplicative error? There's also, a lot more things that can go wrong different ways for covariate measurement error. If you have data that kind of has those properties, then you might want to have a second thought before just throwing them directly into a model. Okay, I think that's all I wanted to talk about today. So, yeah, thank you, everyone. Any questions? Yeah, that's not. Yeah. Yes. Well, if you don't know the measurement error, you wouldn't be able to extrapolate back into the no measurement error case. So yeah, yes, yeah, absolutely. Yes,
Notice that you only use the for linear.
yes.
So those beauty techniques you discussed also apply generally to other extensions of linear models as well?
Yeah, sorry, I should have repeated the question in the thing. Oh, and then theory. Okay, so a question from David. The simulations I showed were all kind of based on linear models, and the question was, do the methods apply for nonlinear models and other models as well, right? Yeah. Yes, they do, I think is the short answer. Yeah, there has been literature. My PhD was actually partly based on that, so I'm pretty sure they do work for nonlinear models as well. And in fact, like this, the final simulation I had there wasn't actually, it was my Y's were binary, and all sorts of departures from normality there. So it does definitely still work, but you do have to be then even more careful about kind of this phenomena where you're doing better than not doing anything, but that doesn't mean you're doing perfectly. Yeah. Yes. Yeah, so if you have if your measurement error isn't too big, and a lot of the assumptions that you're making, such as like normality and stuff, hold, then you're like over here, then you can get the power back, right? With the methods, even with measurement error. But once you start departing from that, so if you have like a lot of non-normality going on everywhere, with your responses, with your X's as well, stuff like that. And if your measurement error is large, then you probably would get a reduction in power, even if you use these methods. But that would be better. That would be better than what you're doing without using the methods at all still. So without using any of the methods to adjust for the error, your power would be very, very much reduced. And with your after applying some of these methods, you might get a bit of power back. So at least it's a bit better. Yeah, but yeah, measurement error can be a reason why you're not getting the results that you want. Okay. I think that's it. Thank you, everyone. Hmm.
Have to get my meeting. This presentation, are you making the slides available?
Yes, they will be.
Did you record it as well? Or?
Yeah.
Okay.
Yeah, it'll be on our YouTube channel very soon, and the slides will there'll be a link to the slides on the YouTube video as well.
Okay, awesome. Thank you so much.